Hello, everyone. So let's discuss chapter 6. In chapter 6, we will learn about energy, rate of, and equilibrium in a chemical reaction. So there are three subtopics which will be covered in this chapter. So first, we will discuss about the energy in a chemical reaction. So what happens to energy when a chemical reaction takes place, and then we'll discuss about rates. So rate is the speed of a reaction over time. Some reactions are slow, some reactions are fast. Why they are slow, why they are fast, and what factors affect the rate of the reaction, that will be discussed in that section. And the last section is the equilibrium in a chemical reaction, and this concept is observed in those reactions which are reversible in nature. Reversible in nature means that if A plus B gives us AB, then AB can also give us back A plus B. So that would be a reversible reaction. Okay, so we'll discuss about equilibrium also. So these three topics will be covered today. Okay, so let's start with the energy involved in a chemical reaction. Okay. So first we'll discuss the energy and chemical reaction. Now, an example of a common chemical reaction is the gas burning in our kitchen ovens. So that gas is the most commonly gas is natural gas, and natural gas is, this is the formula of natural gas, that's methane. So in natural gas, and when that gas combusts, it reacts with oxygen, and the products are carbon dioxide and water. This is the chemical equation. Similar reaction takes place in our car engines. Instead of methane, it combusts gasoline, but the products are similar, again, carbon dioxide and water. This equation is not balanced, by the way. Now, what happens to when we combust gas in our oven? What happens to heat? Does it comes out or goes in? Or is there any heat change when we combust natural gas or methane? Is any heat is involved?
Yeah.
Yes, right? So it heats up. So that, what is heat? Heat is energy. So this is one example of a chemical reaction where energy, in fact, all chemical reaction, in all chemical reaction, there will be some energy. Now that energy can be in, most commonly it will be in form of heat. So heat will either come out, or in some cases it may go in. If heat comes out, the reaction chamber or the surroundings where the reaction is taking place will become hot. So for example, in our kitchen oven, when we burn methane, so the surrounding of that place where the flame is burning gets hot, right? So those kind of reactions are called exothermic reaction. Exothermic means, exo means out and therm means heat. So heat is coming out. There are some reactions in which the surroundings or where the reaction is taking place becomes cold. Why that happens? Because in those cases, the energy or heat is absorbed by the reaction. So if it's heat is absorbed by the reaction, then the nearby area where the reaction is taking place becomes cold. Those reactions are called endothermic reactions. Okay. So the common exothermic reactions are any fuel burning, so, or combustion reactions. All combustion reactions, in fact, are exothermic reactions. Okay. When someone exercises or there are machines, doesn't it say that person would say, I burned that many calories, right? Burn that many calories, right?
Yeah.
So so burning is actually combustion, right?
Yeah.
So what's the meaning of that burning calories means? What does that mean? What do you think? What does that mean?
Mm,
Did that person really burn something? Burn means like set it on fire?
no, like
No.
energy is being released.
Yeah, so that is correct. So that person did not really burn that the anything. What that person is trying to say is that the reaction was similar to the combustion. So for example, in previous slide we saw that when you burn a fuel, methane in that case, in our kitchen, uh, some reaction takes place and then heat a comes out, right? So heat comes out. So this was the case. So when a person exercises or does some work, then again the fuel inside our body, which is food, right? Food combines with oxygen. There is no flame inside, but the reaction is about the same. And then we again get product, some products plus some heat again, right? So in our food, in our body, what is our fuel? Our fuel is carbohydrates, fats, and these are the main actually source of fuel. We do our food does have proteins also, but proteins are mainly used for as a building blocks or repair our body things. Uh, for fuel, for energy, our body mainly relies on carbohydrates and fats. See, so when these molecules, carbohydrates or fats, they combine with oxygen inside our body, that reaction takes place at cellular level. So these carbohydrates or fats break down into smaller molecules. Now, carbohydrate and fats, they have high energy stored in them. So glucose, it's a molecule found in carbohydrates. So you can see here, so the glucose molecule has this much energy, quite a lot, right? This much energy. So in our body, in the cells, these glucose molecules combine with oxygen and they break down. When they break down, so the products are, these are the products, carbon dioxide and water. Aren't they similar to the products which we saw in our previous slide, right? When
Yeah.
the methane was burned? Can you see the similarity between food decomposition in our body and fuel burning in our kitchen? Is there a similarity?
Yes. Products are
Yes.
the same.
So products are similar, right? The other similarity is that heat was generated in this reaction, right? So some heat was generated in our kitchen. Same way, you see the energy. Let me change colors here. So the energy of glucose is this much, but the energy of carbon dioxide and water is only this much, only this much. So less energy. So this is the extra amount of energy which is available for our body to do whatever the body wants to do. So your body is moving, your body is lifting stuff, or performing other work. So your body needs energy. So that's where the energy comes from. So where does it comes from? So glucose. So glucose has extra energy or high energy stored in them. So glu so that energy is liberated when glucose combines with oxygen. So carbon dioxide and water are formed, and plus extra energy comes out, and that energy is available for your body. So remember one thing, that the carbohydrate and fats have high potential energy and carbon dioxide and water has low potential energy. So they have only this much energy, right? So this is the extra amount of energy available for our body every time glucose is consumed. Okay, so that's where how we get energy from our food. So the question you may see in exams or quizzes is, which biomolecules are the main source of energy? Is it proteins? Is it carbohydrates, fats, all of them? What do you think? What is the correct option?
Carbohydrates. B and C.
So let's call this A, B, C, D, and E. So which option is the correct option?
E.
B,
E.
E. And E is correct. Yes, both fats and carbohydrates are the main source of energy. Proteins, I've seen those shows on Discovery where they, oh, there's so much protein and I need to survive on protein. When you are in a survival mode, you really should go for carbs and fats. Proteins are essential for repair of cellular repair and some other uh, important functions. They don't really give that much energy. We'll see later on that fats have a lot more energy stored in them as compared to proteins. Okay, so the correct answer, yes, indeed, it's option E. So both carbs and fats are the main source of energy. And if you look at any food item, you will see the calories stored in that, or the calories obtained when you consume certain amount of that food. For example, in this case, it's Cheez-Its. So from every one serving, how many calories can we obtain? Can you see how many calories? 130
30.
calories. Now, these calories which are obtained from the food sources, these are called nutritional calories. They are different from the normal calories. Let me discuss, let me tell you what the calorie is. So imagine you have a container, it has some water in it, right? So there is some water. And you want to, in let's say temperature of water is some temperature. Let's say the temperature is 21 degrees Celsius. It could be any temperature, right? What if I want to increase the temperature from 21 to, let's say, 25 degrees Celsius? I want to take the temperature of water up. What do I need to do? How can I increase the temperature of water?
Add heat.
Add heat, exactly. So I will put a flame or some kind of a, right, some kind of a flame underneath. So this flame is adding the heat, right? So add heat. So if you add heat into water, the temperature will go up, right? So imagine I have a tiny container, a tiny container. In that container, I have 1 gram water, exactly 1 gram of water. Okay. And 1 gram, exact, that's important. And if I want to increase the temperature of this water by 1 degree Celsius, suppose this is at 20 degrees Celsius and I take it up to 21 degrees Celsius. So what is the delta T or change in temperature?
Find
1
out.
degree. 1 degree, right? So I went, take it up by 1 degree. It could be from any temperature. It could be from 35 to 36, could be from 51 to 52. It could be any, but as long as the difference is 1 degree. So I need to add heat to do that, right? The heat needed to perform this operation, that heat is called 1 calorie. So 1 calorie is a heat which can increase the temperature of 1 gram of water by 1 degree Celsius. That's the definition of 1 calorie. Do you think it's going to be a large amount of heat? Calorie is large amount? It's not. 1 gram of water is tiny amount. It's really small. Okay. Do you understand what's the meaning of 1 calorie?
Yeah.
So meaning of 1 calorie is it's the amount of heat needed to heat 1 gram of water by 1 degree Celsius. Not a lot. 1 degree is not a lot. You keep it outside in the sun, it heats up by 1 degree quite fast. Okay. there is another unit, which is standard unit. That unit is called joules. So 1 calorie is equals to 4.184 joules. So joule is even smaller than calorie. Okay. Now the nutritional calorie, which you see on food items such as this one, so you will see that nutritional calorie is written by uppercase C. So this is nutritional calorie because this is uppercase C. So nutritional calorie is equals to 1000 normal calories. So normal calorie is written within lowercase c. See, this is the uppercase C. So this is the nutritional calorie. This is the regular science calorie or chemistry calorie, you can call it. But that's the calorie. That's the difference between nutritional calorie and the regular calorie. So if your food item like this Cheez-Its, it's saying it has 130 calories per serving. Actually, it has 130,000 normal calories because each nutritional calorie is 1000 calories. Okay, so we'll solve a couple of more problems related similar to those. But do you understand the difference between the normal calorie and nutritional calorie?
Yes.
Yes.
So the problem, let's go over a couple of problems here. Okay, so which unit of energy represents the largest amount of energy? Is it option A, B, C, D, or E? Remember one thing, one normal lowercase calorie is equals to 4.184 joules. And one nutritional calorie is equals to 1000 normal calories. So just remember these two equality statements. So between a calorie and a joule, what do you think? Which one is bigger? Is calorie bigger or joule is bigger?
You.
Okay. So let's say one red large stick is equals to 4 tiny black sticks. Which stick is larger, red stick or black stick?
Red.
So then same logic, if 1 calorie is equals to 4, ignore the decimal and other. If 1 calorie equal to 4 joules, how come then joule is bigger?
Okay. Calorie is big.
So which one is great? The calorie.
1 calorie.
The calorie, right? So between the nutritional calorie and the regular calorie, which is bigger?
Nutritional.
Nutritional. So now we have established. So out of these three, so which is the biggest one then?
A.
Yeah, so the correct answer is A is the biggest amount. Okay, so nutritional calorie is the largest amount of energy. Any question between these three units? Because we're gonna see more problems where these three units are there, and we may have to convert one unit to another. Let's look at another example. Okay, a nutritional label lists the energy content on this food as 70 calories. So these are uppercase calories because these are nutritional calories. How many, well, let me take this out, and lowercase calories. Okay, let me fix the problem. How many lowercase calories is this? Okay, so given, what is given? Given is 70 nutritional calories, see the uppercase calorie. Do we know that one uppercase calorie equals how many lowercase calories?
1,000.
1000, right? We know that. And we want to find number of lowercase calories, right? So can we go from nutritional calorie to lowercase calories with the help of a conversion factor? And conversion factor gonna come from here, right? So let's solve together. So what is, how many uppercase calories are given? 70 multiplied by, so this conversion factor. So what's going to be on top and what's going to be the bottom part of the conversion factor?
1,000 on top.
1000 on the top, lowercase calories, and bottom will be 1 uppercase calorie, right? So calorie with the uppercase C cancel with calorie with uppercase C. And what is our answer?
70,000.
70,000 lowercase calories. And so the correct answer is option A, B, C, D, or E.
E.
Here we go. Can we solve similar problems?
Yeah.
Okay. Let's solve one more. Same problem. Let me extend this problem. Oops, sorry. Now, why don't you guys give it a try? Calculate how many joules is this. So now you need to convert this into joules. And remember, 1 lowercase calorie is equals to 4.184 joules. Give it a try and then we'll solve together, okay? I'm gonna give you a couple of minutes to think about it.
That'll be 292.
Okay, so as long as we have the answer, that's fine. So we'll see if the answer is. Let's work together. Let's solve it together. Okay, so now what we need to do is we already have the lowercase calories with us, right? So we already converted the uppercase calories to lowercase calories. So next is we need to convert the lowercase calories into joules, right? So how many lowercase calories do we have?
70,000.
70,000 lowercase calories multiplied by conversion factor. Do we have a conversion factor between lowercase calories and joules?
Mhm.
We do, right? So down here will be
Joules.
1 lowercase calorie, right? So left hand side up here will be 4.184 joules. So lowercase calorie cancel with lowercase calorie. So 70,000 multiplied by 4.184 equals how much? Do you have calculator? So what do you get when you multiply?
292,880.
2,293.
Oh, 2. Oh, you're rounding it.
Oh, well, maybe I did not hear you properly. What's the answer? 292?
2, 8,
Then
0.
80.
880.
880.
Yeah.
Okay, 880. Yeah, but because we are given only one sig fig, so that should be changed to one sig fig.
So it'd be 3,000.
Yeah, so it
Or
would be
300.
3 times 10 to the 1, 2, 3, 4, 5, 10 to the 5 joules. Okay.
Can you write it as 300,000?
Yes, that would also be, but don't put any decimal anywhere. Yes, 300,000 is also correct. Okay, so can we convert nutritional calories to normal calories or joules if some other problem is given similar to this one? Can we solve those kind?
Mm-hmm.
Any question related to energy or calories in a reaction or a food item? Okay, so let's talk about the exothermic and endothermic reaction. Before we discuss um, exothermic and endothermic, we have to remember the important law of thermodynamics, and that's the first law of thermodynamics. And this law states that energy can neither be created or destroyed, which means energy is conserved. Okay. In this entire universe, energy is conserved. So if you are getting energy from some item, you are just changing the form of energy. It's not a new energy. Okay. For example, if you cooked food at home, in order to cook the food, you need energy. Where did that energy come from? Yes, anyone? From the oven, right? And where did the oven get the energy? Let's say you have a gas oven. Where did the energy came from or come from? From the fuel, right? So, so if you keep tracking your steps, you will see that you are not creating energy. You are just getting energy from some other source, and that source got energy from some another, and so on. Okay. So we said that the fuel had some stored energy, and that stored energy is called the potential energy. So for example, let's say I have a molecule A, let's say this is molecule A, and this molecule combines with another molecule, let's say this is molecule B, and they react with each other. And after reacting, I get some product. This is my product. So the products are AB, AB, right? So molecule A and molecule B, they have some stored energy in them. Let's call this stored energy, let's say molecule A had E1 energy and molecule B had E2 energy. Okay. And the products, what do you think? What will be the energy of product? Yes, anyone? You remember the first law of thermodynamics, which states that energy is conserved. So based on that logic, what do you think? So if A, so it's good to consider energy as money. Let's say the A is a groom and B is a bride. So groom has $100. So E1 is, let's say E1 is 100. And B, which is bride, it also have $100. See, it's always good to consider energy as money. So when they pair up, what will be the energy or money after they pair up? Yes, anyone? They don't. No?
Will it be the same?
Same, well, how much same? 100?
No, like just like of the two reactants added together.
Yes, and that number would be
200.
200. Yes, 200. Or if we talk about energy, then it should be E1 plus E2. Right?
Mm-hmm.
That's the meaning. So technically what we are saying that if our A and B have this level of energy, And when they combine, so when they become AB, so the level of energy remains the same. However, that does not happen all the time, because sometimes the energy of reactant is different from the energy or potential energy of products. So it means that sometimes products may have less energy. So products may have here, so less energy. So product has less energy. So if it's less energy, what happened? Did we destroy some of the energy which was started? So let's go back to that money logic. So if A has $100, B has $100, and after they get married, now they have only $150. So they have less than what they should be. So what happened to the remaining $50? The ones which the ones disappeared. Where did that go?
Probably absorbed.
Not absorbed, given out. So when they married, those $50 were spent or given out to someone, right? Right? So it means if the energy of product is less, so it means this difference, this much, that energy is given out, energy out. Does that make sense? So if they start with certain amount of energy and end with less, it means they gave some energy out. So some energy is lost. Yes? So where did that energy go? That energy go out to the nearby things or nearby surroundings. Okay.
That
So
would be,
yes,
that would be exothermic, right?
that would be exothermic. Exactly. That's where I was coming at. Yeah. So when the energy is given out in a reaction, then that reaction is called exothermic reaction. So this would be an example of exothermic reaction. So in exothermic reaction, you start with more energy and you end with less energy. And that extra energy is given out. Any question about what is exothermic reactions? Everything okay? Yes or no would be awesome. Highly appreciated. Yes or no?
Yes, everything's okay.
Thank you. So if the opposite is true, let's look at an example where it's exactly opposite of what just happened. Okay, let's get rid of this. Okay, imagine that we have another case in which again A and B are reacting. I'll keep the money logic again together. So let's say starting money was 100 for A and 100 for B, but after they are together, after they react, now for some reason they have $300. Now 300 is more than the combined sum of their starting value, right? So how can they have 300 now? What would have happened? Where did the extra 100 come from?
It was absorbed.
It was absorbed. Yeah. So someone else gave the extra 100 to them, right? So 100 goes in and not coming out right now. So in this case, the energy is poured in the matrimony or the reaction, right? So it means that if your starting value of A and B is certain energy level, so this is the starting energy level of your A and B, and when they combine, now the combined energy value is higher than what they started with. So this extra energy, which now because they're higher, so that energy was given in. So energy in means absorbed. Okay, that's the only way that the product can have high energy than the starting value, right? If the product has higher than the starting value, means it absorbed from somewhere. So those kind of reactions are known as endothermic reactions. So in endothermic reactions, energy is absorbed from the surroundings, and in exothermic, energy is donated to the surroundings. But overall, total energy remains conserved. Okay, let's look at some. So remember this concept: exothermic reactions, they release heat energy to the surrounding, and endothermic, they absorb energy from the surrounding. Okay. Let's look at some examples. Imagine we have a car engine which is running. So inside the car engine, the fuel, gasoline is combusted. So that's a chemical reaction. And heat energy is released. So if this is our car engine, right? So inside the car engine, gasoline, gasoline is combining with oxygen, and we are getting CO2 plus H2O. What do you think? Is this reaction producing the heat, or heat is coming out or going in? When gasoline combusts. So what I'm asking, is this an exothermic reaction or endothermic?
Exo,
Yes, it's exothermic
the
reaction,
gas
right?
is coming out.
Yes, because so if I have to draw the level, so if this is the level of gasoline, so the gas E, so the products are H2 or CO2. So is H2 or CO2 level of energy, is it at red position or is it at green position? So where do you think the products will be?
We green.
And you are correct. Yes, it will be at green position now, right? So the products, why they are green position? Because now they have less energy, because extra energy is given out. That's why engine gets hot, right? Similarly, in a biological cell, a glucose undergoes, so when you consume food, right? So when you metabolize your food, you break down glucose molecules. So it's also kind of a chemical reaction. So glucose molecules gets changed into smaller molecules, which will at the end, the products will be again carbon dioxide and water. In that process, again, some heat energy will be liberated, which is used to heat up your body or some other functions, right? So some energy. So that process is also exothermic process. Okay, so both of these are examples of exothermic reactions. Okay. Any question about exothermic or endothermic? Everything okay so far?
Yes.
Okay. Bond energy. Now so we said that when we combust a fuel, this is natural gas, the fuel which we burn in our kitchen, we get heat. It's exothermic reaction, right? So heat comes out. Now we'll discuss about what is the actual source of that heat. So we'll discuss this from bond energy. So you must remember a couple of concepts. So in this reaction, let's look at the reaction which I just wrote. Our first molecule is methane. So methane is carbon, and carbon is bonded with how many hydrogens? 4, right? And then oxygen is bonded with itself, another oxygen, and there's a double bond. these are the Lewis structure and octets. I'm not worrying about the octets for now. I'm just drawing the structures. Plus water is HOH. Okay. Now, in order to complete this reaction, so let's look at the reactant side. So in the reactant side, carbon is bonded with hydrogens, right?
Yeah.
In the product side, now carbon is bonded with what?
Oxygen.
Oxygens. So it means that in order to complete this reaction, what do we need to do? So first we need to break this bond, right? Yes. Then we need to break these two bonds. Yes. Then carbon needs to create a new bond with oxygen two times, right? One on left side, one on the right side. And water will also need to create a bond with oxygen. So can I say that in a chemical reaction, some bonds are broken and some bonds are formed? Would that be okay?
Yes.
And that's actually what happens in a chemical reaction. So in a chemical reaction, some bonds will break and a new bonds will form. Let's say you have a stick in your hand and you want to break it. Do you need to spend energy to break, or you don't need to spend energy to break?
You need energy.
You need energy to break that. So similarly, if you want to break a bond, you need
energy.
Or you need to put energy in order to break the bond, right? So that means breaking a bond, is it exothermic or endothermic? That would make endothermic, because you need to put energy in to break. Energy in. If energy goes in, the bond will break. Hence, breaking the bond is endothermic. Yes? So now remember the first law of thermodynamics, energy is conserved. So it means if going from this to this, you get energy in, so the reverse is energy will come out. So if in order to break the bond, you need to put energy in, so that means if you create a bond, energy will come out. Okay, so reverse is always true. If one way the process is endothermic, the other way it will be exothermic. So hence making a bond is exothermic. So what is bond energy? So bond energy is the amount of energy required to break 1 mole of any given bond type in gas phase. Okay, so that is the bond energy. So let's look at some values. So in order to break carbon and hydrogen bond, how much energy do we need to spend? 414 kilojoules. So you can see that different kind of bonds will require different amount of energy. But one thing is interesting. If we have a single bond and we have a double bond, otherwise it's both carbon-carbon. Do you see the difference? So what can we say between single and double bond? Which are more stronger, singles or doubles?
Double.
Double.
And if we extend the same logic, what do you think?
Triple.
So triple will be the strongest?
Mm-hmm.
And you are correct. But another thing you need to notice is that going from single to double, the bond energy is not exactly double. Is it double, exactly double?
No.
It's not. It's roughly double. Similarly, if you go to triple, the energy for the triple bond is about 837 kilojoules per mole. So again, it's not 3 times, otherwise it will be more than 900 something, right? So yes, as you go from single to double, double to triple, bond energy will go up. So it means those bonds will become more and more stronger. So out of all these bonds listed in this table, which bond will be the most difficult to break?
The last one.
Carbon-carbon triple bond out of these, yes. So triple bonds are harder to break. So I would need to spend the most amount of energy to break that bond. Okay. So if I need to spend most amount of energy to break this bond, so opposite is also true. If I create a triple bond, right? So carbon, carbon, it create a triple bond. If they create, then I get most amount of energy out also out of this process. Opposite is also true. So it means that if I'm making bonds in a reaction and I make in one reaction, I make this bond, let's call this reaction number A, and in reaction or A, and in reaction B, I'm making this bond. So in both of these reactions, because I'm making the bond, I will get energy out. So it means both of these reactions will be exo or endo. Yes, the energy is coming out. So they will be exothermic. But reaction, which one will be more exothermic, reaction A or reaction B?
B?
B will be more exothermic, yes. Because I need more energy to break the CC double bond. It means if I create the CC double bond, more energy will also come out. Okay. If in order to break CC double bond, I get 611 kilojoules of energy. So if I make CC double bond, how much energy will I get out? Exactly the same amount, 611 kilojoules. Okay. So if I create a CNH single bond, how much energy will I get out?
414.
404. Exactly the same amount, which is 414, which is needed to break it. So whatever energy is needed to break the bond, same amount of energy comes out if you create the bond. Do you understand the concept? Do you understand the logic? It's exactly the opposite. If you break, energy goes in. If you create, energy comes out. Same amount. Why same amount? Because that's the first law of thermodynamics. Energy is conserved. Okay. So what have we learned from these trends? So we learned that higher bond energy means stronger bonds. Okay. Compounds with weaker bonds are more reactive, because if the bonds are weaker, they are easy to break, hence they are easily react with the other bonds. Triple bonds are stronger than double bonds, and double bonds are stronger than single bonds. So same concept. Okay. Let's go back to the same methane reaction. So in methane, so we said there are 4 hydrogens, and then we have oxygen, and then we had carbon dioxide plus water. So in this reaction, first we need to break the bond. Right? Can you tell me how many bonds do we need to break?
4? I mean 6?
If you are considering double bond as 2 bonds, yeah, then 6, but in terms of bond energy, they are just considered 1. Yeah, so we need to break from here. That's 1, that's 2, that's 3, that's 4, and this 5. So we are breaking 5 places. Let's say places, right?
So a double or a triple bond is only counted as 1 bond?
Yeah, but the energy is more to break them, but it's still 1 bond.
Okay.
Okay, so if you go back here, so this 611, that's for together double. It's not like you have to spend 611 2 times. No, it's just only 1 time 611. So for triple, you need to spend 837, and all 3 will break 8 with 837. You understand? Mm-hmm. Okay. So it means we are breaking bonds 5 times. So 4 CH bonds are being broken, right? What else is being broken? one OO double bond is being broken. So in order to break that, we need to spend energy. Spend energy means energy in, right? So energy in or endothermic. Are you okay so far?
Yes.
Okay. So let's say what new bonds are being made. I'll use the color green for making the bond. Okay, so what new bonds are being made? Yes. Do you see any new bonds which formed in this reaction?
No.
Yeah.
Yeah, and which one is that?
Carbon with oxygen and then
Yeah, so we have
ox-
this new bond, right? We have this new bond, and we have this new bond and this new bond, right? These four bonds are, so how many carbon and oxygen double bonds are formed?
two.
2 CO double bond. And how many oxygen and hydrogen bonds are formed?
Two.
2. So in when the bonds are formed, what happens to energy? Energy comes out or in? Energy
Um,
comes
out.
out, right? In breaking, it goes in, it's endothermic. In making, energy comes out, it's exothermic. So in overall this entire reaction, when you break the bond, some energy goes in, and when you make the reaction, make the bonds, energy comes out. So that overall, this heat change, delta H is the heat change. So delta H is the sum of all the bond energy being broken plus the sum of bond energy being formed. Imagine, I'm just giving you some examples, okay? Not true number, I'm not gonna give. Imagine in order to break carbon and hydrogen, just random numbers. So let's say carbon and hydrogen, you need 1 unit of energy to break it. Carbon and oxygen, you need 2 units. Carbon and oxygen, you need, maybe it's again 2 units. I'm just giving some random numbers, okay? These are not true numbers. Hydrogen and oxygen, let's say this is also 1 unit. Okay. The equation is not balanced, by the way. So in order to balance the equation, we need to have 2 here, okay? This will also break, and 1 CO2, and we're gonna get 2 waters. This is when you balance the, oops, sorry. When you balance the equation, this will be it. So oxygens here will be, so instead of 1, there will be 2 OO, so that will remain the same, and it will be 4 OH bond. Why more number of molecules? Because the equation was not balanced. If you count, all atoms are balanced. So there are 4 hydrogens, 4 hydrogens, 4 oxygens, 4 oxygens, and 1 carbon. Now it's balanced. So imagine in order to break this bond, all these bonds, right? You spend 100 units of energy. Let's ignore whatever I was writing. So ignore this section. So I'm just gonna combine. Imagine that we spend 100 units of energy. And when these are liberated or when these are formed, let's say I get 150 units energy out. So what do you think? This reaction, will it be exothermic or endothermic?
Exothermic
It will be exothermic. And why it will be exothermic?
because energy is released.
Yeah, so because less is going in, but more is coming out, right? So 100 was going in, but coming out was only 50, coming out was 150. So the 50 units of energy was extra. So hence that makes it exothermic. So we need to look at the sum total of all energies being broken and being formed. If the total energy spent to break the bond is less than the energy created by making the bond, then the reaction will be exothermic. The simple, so what in, so we call it change in heat delta H reaction. So this is equals to the energy of reactant uh, minus energy products. In previous case, energy to break the reactant was 100, yeah, minus what was the energy which was created, 150, right? So what is delta H reaction for previous example? 100 minus 150, the answer will be negative
minus 50.
50 units. And we said it's a exothermic reaction, right? Because more energy was coming out. So we can say that delta HX reaction will be negative, the reaction will be exothermic. If it's positive, the reaction will be endothermic. Okay. Any question?
Those
So
weren't
what
the,
yes,
those weren't the actual numbers, right? Like
those
for,
were not the actual numbers.
okay.
Those were just an example. Actual numbers you can get the numbers from this table and you can calculate yourself. Okay.
Okay.
So this formula, I mean, that's the formula.
Uh,
Formula.
formula is, there is no formula, is this is the formula. Energy of
Yeah.
reactant minus energy of product. Yeah. So you
Yes.
just calculate how much energy you consumed in the reactant side and how much energy you produce in the product side. Just take the difference. If difference comes out to be negative, then your reaction is exothermic. If the difference comes out to be positive, then the reaction is endothermic. And the energy of bond energies you can get from this table. But make sure you account for all the bonds, which kind of bonds are being broken, which kinds of are being formed. Okay. And the equation must be balanced. Okay, so let's look at energy diagram. So as explained earlier, if our reactant has energy level up here and products has energy level down here, so our products has less energy, right? And reactant has more energy. So if you go from reactant to product, now you're losing energy because you are going from high energy to low energy. So this is low energy, right? So this is high energy. This extra amount of energy is heat release, this much energy, this gap. So this reaction is exothermic reaction. In endothermic reactions, your reactant will always be at low energy and products will be at high energy. Okay. And when you go from here to here, you need to absorb energy because now you're going from low energy to high energy. So you need to absorb this much energy. Hence, this reaction is endothermic reaction. Okay. I'll explain what those hills means. Okay, in a while. You see these big hills? I'll explain in a while what they, ignore those hills for now. So for now, just remember where is the position of your reactant, where is the position of your product. If your reactants are high and products are low, the heat energy is released because you are going from high energy to low energy. So you have to release this energy, hence the reaction exothermic. If you go from low energy reactants to high energy products, you need to absorb this much energy. Hence the reaction is endothermic because you are absorbing it. Right? Any question about, so what's the meaning of this energy diagram? These are called energy pathway diagram or energy diagram. Everything okay?
Yeah.
Okay. Let's check if you understand. So ignore those hills for now. I'll explain what those means, but just remember the position. Let's say I have a reaction A, and in this reaction A, my reactants are here. I'm using the symbol R for reactant and P for products. And my products are here. In reaction B, my reactants are here and my products are here. Right, so this is my product, this is my reactant, and in reaction A, this is my reactant. Is reaction, so first, is reaction A exothermic or endothermic?
Endo.
Endo. And you are correct. It is endo because products are high, so reactant has to absorb energy. You are correct. How about reaction B? Is it exo or endo?
Endo.
Say that again.
Endothermic.
And you are again correct. This is also endothermic because again, the products are higher than reactant. So reactant must absorb energy to go all the way up, right? Energy absorbed, which means endo. But if I compare A and B, which one is more endo? More endo
B.
means which one would need more energy to complete?
That'll be
Which one?
B.
And you are again correct. See the difference? So you compare the gap between reactant and product. Bigger gap means bigger energy is needed to complete. So more endo. Okay. Is that concept okay? Yeah.
Yes.
Okay. Let me
Yeah.
ask another one. This chapter does not have many math problems. It's just the conceptual kind of problems. Let's say I have a fuel, two different kind of fuels, and when they burn, the energy sort of looks something like that. So let's call this fuel A and fuel, I'll use different color. Okay, let's talk about fuel A. Because it's a fuel, and when fuel burns, so what do you think? The reaction will be exo or endo?
So
It will be, it has to be exo. That's the meaning of fuel because it gives the energy out. So the fuel A, the reactant side is here, and the product is, will it be more than the reactant or less than the reactant?
yes.
Less. So let's say this is the P. And in fuel B, let's say this is fuel B. So that's reactant and that's product. Which fuel is better? Fuel A or fuel B?
What do you mean by
Better caloric value. Caloric value means amount of heat released per unit of fuel burned. Which fuel is better? A or B? Or they are same?
A.
A is better. And what is your logic? Why do you think A is better? And don't worry, if you say B, I'll ask the same question again. Why do you think B is better?
A is better because the energy that is released, it's, well, I mean, comparing it with B, energy released in A is more, I don't know how to say. So comparing to both of them, fine, energy is released in both of them. But
yeah, both of them are releasing energy. All fuels, when you burn, they release energy. You're correct. Yes, both of them are. Now we have to compare if A is better or B. So normally we say the fuel which gives more energy is a better fuel, right? You want as much heat as possible when you consume that fuel. So which one is giving you more energy, A or B?
A.
A. Everyone agrees with option A, or anyone has other? B, and why do you think B is better?
Because there's a larger difference between the reactants and the products. Therefore,
Uh-huh.
energy is being released.
Yes. So that was the yeah, that is correct. So pay attention. Yes, you may think P is higher here, but that's not what we are getting. We are getting from here to here. This gap is the energy which is released. So that much energy is released. Not this one, not the gap shown with blue. That's not what we get. We get this gap. So look at here. In this case, energy is this much energy comes out. So is the gap between reactant and product bigger in B or A?
B.
B, bigger gap means more energy comes out. So fuel B is better. Just compared to the caloric values, or the it may not be better, because what if the fuel B is more expensive? It may not be better in all aspects. Okay. But just looking at the amount of calories, fuel B is better because it's giving us more calories when it reacts. Any question about energy diagram so far? Okay. So energy diagram, you can tell by looking at it if the reaction is going to be exothermic or endothermic. In exothermic reaction, your reactant, in exothermic reaction, your reactant will be high and your product will be low. So you go from high to low, energy goes out. So this will be exothermic reaction. So this will be exo. So the products have lower energy than reactants. In endothermic reactions, so your reactants will be low, products will be high. So you go from low to high. So you need to absorb energy in. So this product energy will be higher than the reactant. And the overall energy of reaction is again energy of product minus reactants. So you can calculate how much energy is released or absorbed. Okay. Let's look at some examples. Combustion of propane. So that's the same gas which we use for barbecue cylinders. This is the formula of propane, C3H8, and that's the equation. So in this reaction, heat on the product side. So products are things which are generated. So it means heat is also produced. So heat produced means heat comes out or heat out, right? So that means this reaction is exo or endo. Is it exo or endo?
So
This is exothermic. Yes, and it is exothermic. Okay. Now, let me get rid of
So
this.
it's exo
So
because
if I have to draw the diagram, yes, I mean, you had a question?
so is it exo because the heat is being released?
Yes, it is exo because the heat is being released. You're correct. So if I have to draw the diagram, energy diagram, where do you think the reactants, these are the reactants, where should I draw the reactant? Up on the top or somewhere down on the y-axis? Okay, so let's say the reactants are here. Okay, so this is a reactant. So reactant means C3H8 plus O2. These are my reactants. Now products, if I have to draw the products, which are CO2 and H2O, are they above the reactant or below the reactant in diagram?
low.
Low. Would that be okay here? And that is correct. So this gap from the reactant to product, so this is the amount of heat. This is the gap, right? This is the energy which is released. And how much is that value? Negative means it's coming out. Okay, so it is releasing 2010 kilojoules per mole. either you say negative 2010 or you say 2010 kilojoules released. Release means coming out. See, if you go to your bank and take some money out, in the bank statement, they will put negative. Like if you take $100 out of your account, if you read the statement, it will show negative 100, means you took money out. Same way, energy, when the energy comes out, the symbol negative is used because it's out of the system. Right? Any questions so far? Okay. Now imagine you are enjoying with your family and doing barbecue and you want to cook some burgers. So in order to cook burgers, you need heat energy, and you get heat energy from combustion of that propane gas. So when you open the gas cylinder or knob, do you start getting energy immediately? Now, do you need to do something before you get heat out of
You have to ignite it.
You have to ignite it, right? So what is the meaning of ignition? So how do you ignite it?
With fire, which is heat.
So it means in order to start this reaction, you need to put some heat in the beginning. Not all the time, just in the beginning, a tiny bit, not a lot of heat, right? So that process is, so it means your reactants are here. So they're not gonna go like that immediately as soon as you open it. That's not what happens. So in the beginning, you need to ignite. So ignite is ignite with fire, little amount, tiny amount. So what is that fire? That fire is energy. So you are putting some energy in. So it means you start the reaction. So you put some energy in. So this reactant, so when you ignite it, you put energy in, the value of energy goes up. So once they reach at a certain level, and then it goes all the way down. So this is the amount of energy required to ignite, so activate. So this is known as activation energy. Okay, so this is tiny hump you have to cross. If you do not cross this hump, the reaction will never start. So that's why if you do not ignite, reactants stay on the reactant side, products will never form. So cooking will never start. So it means in order to initiate any reaction, you need to initially give some energy in, right? So that energy is known as activation energy because it needs an initial spark to ignite. Okay. Now, imagine you have two fuels. One is propane. Have you ever used propane? You guys? It's just like natural gas, just like at home. And the other one is charcoal. They are both exothermic. It means they both gonna give this. So products will be down here, reactants will be up here. Both are exothermic. Now, which one is easier to work with or ignite?
Propane.
Propane. And you know why propane is easier? Because in case of propane, the activation energy is tiny. You need just a spark, tiny spark, and the reaction starts. And then, so this activation barrier is small. So small activation barrier means you need a tiny amount of energy to start the reaction. However, in case of charcoal, the activation barrier is huge. It's quite big. So you need a large amount of fire to begin the reaction, right? So that's why charcoal takes a while, because you keep heating the charcoal, keep igniting the charcoal, and eventually it will. And then the reaction, once it starts, it starts. So it means you need to push charcoal beyond this hump energy barrier. So this much energy you need to start in the beginning. Once you take it there, then it just downhill afterwards. So then it starts. So it means if the activation energy is low, the reactions will be easily, the reaction will easily begin, and then we can easily get the products. But if the activation energy is high, it will take it some time to begin the reaction. Okay. Question so far? Everything okay? Okay.
Can you go back to that last slide really quick,
Mhm.
please? Thank you. Okay,
Yes.
got it.
Now, if you see heat energy on the reactant side, that means you are inputting the heat energy in, so which means heat is being absorbed or consumed. So these kind of reactions are known as endothermic reactions, and the energy is value will be denoted by a symbol positive. Again, when you submit or put money in your bank account, again the value, it will show up as a positive quantity because you uh, deposited it inside your bank account. Same concept with energy. So if I have to draw the energy diagram of this reaction, so imagine if my reactant, which is Al2O3, is up here, where will be my product, above or below? Remember, it's endothermic reaction, so my product will be high up, aluminum plus oxygen. Okay, and again in these reactions also there will be activation energy requirement, so it's not like they're gonna go right here. That's not what's gonna happen. So you need to again heat them up. There will be barrier, you cross the barrier, and then it will, so this will be the activation energy. Endothermic reaction usually have high activation barrier, quite large. So that's why you need to heat them up quite a bit to accomplish that change. Okay. So remember the sign, positive or negative. When the heat is released, we use the negative symbol. When the heat is absorbed, we use the positive symbol. Okay, predict reaction A. Is it exo or endo?
The first one is
First one, A.
exo.
Endo.
That's the important word.
Oh,
Yes.
endo.
When the heat is absorbed, it's always endo, so the reaction is endo. Yes, endothermic. How about reaction B? Exo or endo?
Endo.
Again, positive symbol also means heat is being absorbed, so it is also endothermic. You are correct. Any question about exothermic, endothermic, energy diagram, activation barrier? Any question at all? Okay, so let's go with option C now. Some hypothetical reaction. So reactants, product. Is this reaction exo or endo?
And endo. I'm not sure if they're on the same level though.
Yeah, so products are higher up, right? So yes, it is endo.
Endo.
Exo.
Exo or endo, this reaction?
Exothermic.
It is exo, yes. So your products are lower than reactants, yes. So that would make it exo. Okay, so any question about any of these concepts, exothermic, endothermic? energy diagram.
So what type of questions do we expect to see? Is it just, this or,
Something similar to this.
okay.
Did you take the quiz on Canvas?
I mean, for chapter 6?
Yeah, I think last night I opened, maybe it opened. So you have until Wednesday to take it. So you will see what kind of questions can be asked.
I'm taking the quiz.
You have 3 more days to take the quiz. That's just to give you an example of questions. Okay. And it will be similar to what we have discussed so far. Okay, so which statement is false? A, B, C, D, E. Yes. Which statement is false? Let's go one by one. A, energy released when bonds are formed. Is it true or false?
True.
True.
And you're correct. It is true. Because energy is absorbed when you break the bond. So opposite is true, so which is exactly what it says here. Next, B, bond making is exothermic. And you already said energy released when bonds are formed, right? So that makes B, if A is true, that means B is
True.
also true. If energy is released, so that's exothermic, that's also true. Let's look at C. After a bond is made, the atoms connected by the bond have lower potential energy. Okay. So imagine A and B gonna make a bond, AB, right? So in this process, energy is released or absorbed?
Release.
We just said energy is released, right? So energy is released, go out. So if energies go out, now A and B, do they have more energy than before or less energy than before?
Less.
Yeah, they have less, right? Because they release some of it. So would that be, so the atoms connected to the bond have lower potential energy. So is that true or false now?
True.
False. False.
Why would that be false? Remember, A and B has some energy, let's say 100. They connected and out of some energy was released. Maybe, I don't know, 50 was released or some. So now A and B has low energy or high energy than before making the bond.
Higher.
They released it. So if they have $100 in the beginning and when they connected, they lost 80 out of it. Now they have more money or less money?
Less.
So less means low, right? Same thing with energy. If they lost some energy, now they have low energy or high energy. They lost it, remember.
Okay. Lower energy.
They have lower energy. So that makes statement C true or false?
True.
True. How about D? It takes energy to make new bonds. Do we have to spend energy to make bonds?
False.
That would be false. We don't, it doesn't take energy, it releases energy. So you already found the false statement, so no worry about E, but E is also true because delta H less than 0 means negative. Negative means exo. So we know that when bond is made, it's exo. So that would also be true. Okay. So these kind of questions can also be asked. An energy diagram for a reaction, the products are shown at a higher level than the reactants. what must be true? Okay, so remember, products are shown at higher level than reactants. Remember this, products are higher than reactants. So which statement is true? Let's say the first statement, the reaction absorbs energy to form the product. Is it true or false?
True.
False.
True.
All the products are higher.
Yes, is it false or true? First statement.
True.
It is true, because it says that the products are higher than the reactants, right? So it means from here to here, energy is absorbed, right? So this is true. Second statement, it is exothermic. True or false?
False.
It's not exothermic. Absorbed is endo. Delta H is less than 0, means it's negative. Heat change is negative. Is it true or false? False. Negatives are exothermic reactions, so it's false. Potential energy has decreased. Did energy decrease in this reaction?
No.
No.
It increased, in fact, right? So it's false. The products are more stable than reactants. I don't know if you read in this chapter earlier, but high energy means instability. Everything wants to be as little energy, as lower energy as possible. So having more energy makes the molecule more unstable. So this is, products are more stable, which is false, because products have high energy, so they are unstable. High energy is unstable. Okay. Things break when you add more energy to them. So they become more and more unstable. Okay, so that's all about energy in a chemical reaction and energy diagram. Any question related to any of these topics? Everything okay?
Yes.
Just like the chemical reactions in a test tube or in a chemistry laboratory, we also have chemical reactions in our body or biological systems. Those reactions are called metabolism. So when the food we consume inside our body, chemical reaction takes place. The food item breaks down into smaller molecules. So we call this metabolism. Okay. So just like any fuel, when it combusts anywhere outside, it produces energy. Same way, when the food is consumed, it will release same amount of energy. So in our food, these are the main components: carbohydrates, proteins, and fats. And these components can give us energy. There are some other components like vitamins and minerals. They don't really give any energy. They have some other functions. But the important number is how much energy per gram we can obtain from these items. And you can see that fats have more than double the amount of energy compared to carbohydrates and proteins. Carbohydrates and proteins both release 4 nutritional calories per gram, but the fat release 9 nutritional calories per gram, which can be a good thing and can be a bad thing also. Okay. About fats. So if someone is really starving and needs lots of energy to, survive, then fat is a good option. But in some other cases may not be. So you may get these kind of problems. A food label lists the following: 22 grams of carbohydrates. So in the food label given, how many carbohydrates are there? 22 grams, right? How many fats are there? Anyone? And how many proteins?
5
Proteins are 5 grams. And what do we want to find?
calories from the carbs.
Calories from carbs. We only want to know calories from carb. The other are extra. You don't even have to worry about it. So on the side, do we know when, let's go back here. Calories per gram, it means for every 1 gram of carbohydrate, how many calories do we get?
4.
4, that's what it means. So it means when we burn 1 gram of carb, it gives how many calories? 4 calories. Yeah, so that's where it comes from. So that's the meaning of calories per gram. For every 1 gram, we get 4 calories. That's nutritional calories, by the way. So we can use this as a conversion factor. So now we need to convert grams of carb to calories. How many grams of carb do we have? 22 grams, right? So 1 gram, and on top will be 20, oh, sorry, not 22. 4 calories. That's the conversion factor, right? So grams and grams cancel. So what is the answer?
88 calories.
So the correct answer is
Calories.
88 calories.
I think we've done something like this in the lab.
Yes, we in a normal semester, in fact, we do calculate calories in peanut or calorie. Last time we did calculate how many calories are there in Cheetos. We burn the item and we capture how much heat is there, and then we divide by the grams and all those things. We do, in fact, we do it, but unfortunately, this semester we are not gonna be working in the real lab. So this experiment actually is quite interesting. Any question about how to solve this kind of problems? So similarly, if I ask you in the same one, if I ask you how many calories are there from fat in the same food, can you calculate calories from fat now? We just did calculate calories from carb. Now, how about you guys give it a try and calculate calories from fats? And let me know what you get. And remember, 1 gram of fat gives how many calories?
9.
Yes.
Is this 63?
That is correct. So if you want to calculate calories from fat, so grams of fat to calories. So how many grams do we have? 7 grams multiplied by 1 gram down here and 9 calories up here. So grams and grams cancel. Is it visible? I'm writing right at the bottom. Can you please confirm if it's visible?
Yes, sorry.
Yes. So 63 calories from fat.
Are you gonna go over chemical equilibrium?
I was planning to. Oh, it's
because it's
yeah, it's okay. We can extend. It's not. Okay, so I'm gonna quickly explain what is a biochemical pathway. So biochemical pathway is a sequence of reactions in a biological system which will end up to some product. So for example, imagine if we reacted A and B and that gave us AB, and then AB broke down to give us C plus D, and then C plus D gave us something E. So see, this is a pathway. So in a pathway, so that's reaction number 1. In reaction number 1, our product is AB. That's our product, right? Yes. So, and now this is reaction number 2. So whatever the product was from reaction 1, that became reactant in reaction 2. And now this is reaction 3. So the product of reaction 2 became reactant in reaction 3. So that's called a pathway. It's just a general diagram, but that's what a reaction pathway is. So reaction pathway is a multi-step process or multi-step reaction product. So each step will give you a product, and that product will give another reaction, and so on. So in let me get rid of this. So there are two kinds of biochemical pathways. So biochemical pathways are those reactions that takes place inside a living organism. So there are two kinds of biochemical pathway. First one is called catabolic pathway, and the second one is called anabolic pathway. In catabolic pathway, bigger molecules break into smaller molecules, and in anabolic pathway, smaller molecules join to make a big molecule. Okay, so catabolic is generally associated with digestion or breaking down of our diet, breaking down of food molecules from our diet, and this process generally will be exothermic. They will release energy. Anabolic pathway are observed in building larger molecules such as protein or DNA or lipids from the smaller molecules, and these processes, anabolic pathway, are generally endothermic. So when you eat something, so we have carbohydrate, protein, fat, they break down into smaller molecules. So this pathway is called catabolic pathway. It's exothermic, so energy is released. And these small molecules will sometimes are also used to repair broken down cells or layers or skin. See, if you have a cut on your skin, it heals up. How does it heals up? Because your body is repairing it, making new cells there. So that making of new cell, that process is called anabolic pathway. So skin is your membrane. So that cell membrane, DNA, protein, all those. So these are large molecules. In order to accomplish that, you need energy. And hence this is endothermic reaction. Question about metabolism and pathways, catabolic or anabolic? Any question? I want to cover the equilibrium, so I'm not gonna spend a little bit extra time here. Okay. So we already discussed about activation energy. So this, so that's the same thing. See, activation energy. Let's call this reaction A and let's call this reaction B. Which reaction has higher activation energy, A or B? Anyone?
B.
And B. And B, you can see it also an endothermic reaction. So we can generalize that generally endothermic reactions will have higher activation energy. Both of these reactions, reaction A and B, both of them are exothermic reactions, right?
Mhm.
Which one will be faster reaction?
B, because the activation.
And you are correct. B will be the faster reaction because the activation energy is small, just like the charcoal and the propane. So you need less energy to initiate the reaction. So B is faster. So which statement is true? Fast reactions have high activation energies. That is incorrect, right? Fast reactions don't. Slow reactions have low heat of reaction. That's also not correct. They have high. Slow reactions have low activation energy. That's also incorrect. Fast reactions have low activation energy. This is correct. That's also not correct. So that's the correct statement. Okay, so which one is the correct answer? A. Reaction A is exothermic. Is it true?
Um,
No.
No, that's not true. Reaction A is slower.
Yes.
That is true because it has high barrier, right? So large barrier. This has small barrier. That is true. Reaction B is exothermic. Is it true or false?
False.
False. Reaction B is slower.
Um,
That's also false because B has a smaller activation energy, right? Both reactions are equally fast.
no.
No. Factors affecting the rate of reaction. So rate of reaction is how fast any given reaction is with respect to time. There are three main factors which can affect the rate of reaction. First one is concentration, second is temperature, and third is catalyst. Concentration. So when you increase the concentration, rate will go up. Why it will go up? Imagine this is a reaction chamber and you are reacting molecules A with molecules B. B are red, right? So they are giving us this product. Okay. Now I have another container, and in that container I have a lot more A's and a lot more B's. Now you can see in first container, we have very few A molecules and very few B molecules. In order to react, they need to combine, they need to hit each other. They need to, come in contact with each other, right? These are called collisions. They need to collide with each other. Oops. Anyway, I would have gone. So what do you think in chamber number 1 or chamber number 2, where will be more collisions between A and B?
Two.
Chamber 1 or chamber 2?
Two.
In chamber 2, if more collisions means they are more likely to react in chamber 2, right? In chamber 1, they may not even find each other. So what can we say? If we increase the concentration, the reaction speed will go up or down?
Reaction speed will increase.
Increase there. Yeah. So in concentration, high concentration means high rate. High rate means more speed, right? Temperature. So what's the effect of temperature? Again, in temperature, molecules, they start moving faster. So as you increase the temperature, their speed goes up, right? So they start moving faster. If they are moving faster, are they more likely to find each other if they're moving faster? Yes. If they're moving slower, they are less likely to find each other. And even if they collide, they may not even cross the barrier. So remember, they have to cross. So when they collide each other, they need to cross this barrier. They need more energy. So high temperature means this energy is available at high temperature. At low temperature, this activation barrier may not be available. So hence, as you increase the temperature, the rate of reaction will also go up. Presence of catalyst. So what catalyst does is, imagine if this is the reaction without catalyst. And the same reaction, if you add catalyst, the reaction starts going this way. So red is with catalyst. So what happens with and without catalyst? So with catalyst, how much is the activation barrier? And with catalyst, the activation barrier is small or large?
Smaller.
Smaller. So when you add catalyst, they provide a different pathway for the reaction. They don't participate themselves in a reaction. They don't react themselves. They just provide a different pathway. So that pathway has a smaller activation barrier. If the activation barrier is smaller, what will happen to the rate of reaction? Will it go up, increase, or decrease?
Increase.
It will increase. So all these three factors will increase the rate of reaction by having some effect on activation energy.
So the catalyst isn't a part of the chemical reaction, right?
No, it itself is not a part of chemical reaction. It just provides a different pathway with lower activation barrier. So it just makes the reaction go fast.
So, okay.
Okay. Okay. Okay, so final topic, which is reversible reaction or equilibrium. So equilibrium is observed in reversible reaction. For example, if this is our reaction, if it's a reversible reaction, you will notice this kind of arrow, which is double-headed arrow. So this arrow means that the reaction can go to the right side, or it can also proceed to the left side. Okay, so this direction is called forward direction, and this direction is called backward or reverse direction. Okay, so nothing else changes, just the direction of reaction changes. So if my forward reaction is this one, plus 3H2 gives ammonia. So what will be my reverse direction? I just flip the reaction to the other side. So which will be ammonia now gives me back nitrogen plus 3 hydrogen. So what is my correct option? That will be the reverse reaction. Okay. So many chemical reactions are reversible. For example, this case, hydrogen plus iodine. In forward direction, it gives me hydrogen iodide. In reverse reaction, hydrogen iodide will break apart to give me hydrogen and iodine back. So what happens is that these two combine to give me this one, then this one give me back this one. Will there be ever a point when I get rid of, when I only have HI in this reaction? Will there be that point ever? And the answer is no. It will never be that point, because as soon as you get HI, HI will give me back hydrogen plus iodine. So reversible reaction, you can never get rid of reactants and products. There will be always some equilibrium. Equilibrium is a state. Okay, let me explain the equilibrium. Let me explain with some example. Imagine the same reaction or some reaction. Let's say A plus B gives me AB, and then AB break down, give me A plus B. In the beginning, let's say you have in a test tube 100 of A. So you have a test tube and you have only A, and then you mix B into it, and this reaction starts. So imagine we start with 100 A in the beginning and 100 of B in the beginning. In the beginning, do we have any AB?
No.
No. So AB is 0 in the beginning. So when they react, imagine out of 100, 10 of them react. So what is left over? 90. What is left over? 90, because 10 and 10 react. And how many will I get AB? Right? Yes?
Yes.
But because this reaction is reversible, imagine half of those go back, break down. So we got 10, but out of 10, 5 break down. So 5 break down. So what actually I got? 95 and I got 95 here and 95 here. Out of 95, 10% again go forward. It's always 10% go forward and then some percentage go backward. So 95, 10% goes forward means now I have, leftover is 86, and I got about 14 here, right? And then some of them go back. So this will be 89, and that will be 11, right? And then go forward again. So that will be 79, and this will be 22 and some. So you can see slowly they are decreasing and slowly this is increasing, right? Can you see from these numbers?
Mm-hmm.
But other thing, you will see that the increase is slowing down and eventually at certain percentage, let's say 62, and that's 38, whatever goes forward, same comes back. So then the number does not change. So that stage is known as equilibrium. So at equilibrium going forward, so maybe 10 go forward and 10 comes back. So the overall number never changes. So this is known as equilibrium stage. Okay. At equilibrium, the number of the amount of reactants and amount of products will never change, because that whatever reactants go to the product side, same number of products come back to the reactant side or break down or give you reactant. So that is known as equilibrium. So when the rate of forward direction equals the rate of reverse reaction, right? So the concentrations of reactant and products are constant, then it is known as equilibrium. Is that okay?
Yes.
So at equilibrium, remember rate of forward direction. Oh, which one is correct? Rate of forward direction is faster than the rate of reverse reaction. That's incorrect. We said both rates are equal. At equilibrium, rate of forward is slower than the rate of reverse. That's also incorrect. At equilibrium, they are equal. Rate of forward and reverse reactions are equal. Is that okay?
Correct.
That is correct. Rate of forward, that's not, they don't become zero. They keep going forward and backward. They never become zero. Okay. How about you tell me which statement is correct? 1, 2, 3, and 4.
2.
That is correct. Wonderful. Yes. So the concentration, they become constant. Remember, they don't become equal. See, if we go back, they are not equal. Products are not equal as reactants. Reactants are 62, products are 38. They don't have to be equal, but they are constant. Constant means that they're not going to change anymore. Okay. So that's the important distinction.
So it's not the same. They're not equal, but it's just not changing anymore.
Yes, you are correct. So they are not equal. Reactants will never, in some cases, they may be equal. That may be there, but that's not the point. The point is the concentration will remain constant.
Okay.
So once a reaction is in equilibrium, we can do something, we can alter the equilibrium. And that is explained by a French scientist, Le Chatelier. So he I'll explain his principle with the help of an example. So he said that equilibrium can be altered by disturbing it. How do we disturb it? We can disturb by adding or removing a reactant or adding and removing a product. How does that happen? So you can imagine this as a pressure. Imagine this side is at same pressure as this side. Imagine, right? And they are connected with a pipe. If you put something in, right? If you put something in, so now there is more pressure, right? More pressure, right? So what will happen? It's gonna release some pressure to that side, right? Yes?
Yes.
So the reaction will start going towards this side. So that's exactly what Le Chatelier's principle is. If we add more reactant to it, so we are increasing pressure on this side. So the reaction will shift to equilibrium, will shift towards the product side.
So think of it like a balance almost.
Think of it exactly. Think of it like a balance. Yes, that's a wonderful example. So it's exactly like a balance. So the equilibrium is at balance now. So they are exactly equal. So if you put something here, of course, the balance will alter, and now the reaction will, in order to rebalance it, you need to have more product to create the balance again, right? So the reaction will shift towards product side. Similarly, if we remove something, and then we are removing means we are lowering the pressure. If you are lowering the pressure, so the things will start moving towards left side. So the equilibrium will shift towards the left. Okay. Same, if we add more product on this side, so more pressure here, equilibrium will start shift to the reactant side. If we remove the product, less pressure here, so then the equilibrium will move towards this side. Now, what's the meaning of moving the equilibrium? Okay, moving the equilibrium, means, imagine this is a reaction. If we add more nitrogen means now what will happen? The equilibrium will shift towards product or reactants, or nothing will happen. We are adding more nitrogen into it.
It'll shift to the product.
Shift to the product or shift to the right. So this is our correct option, right? Shift to the right means, imagine that at equilibrium, imagine, I'm just guessing, imagine there is 58% nitrogen, 58% hydrogen, and then remaining, that's 42% ammonia, right? That's at equilibrium. Imagine if we add more nitrogen, now shifting to the right means we have more ammonia. More ammonia means it may be now 48% here and 52 here, 52 here. That's the meaning of shifting to the right. Shifting to the right means the quantity of product will be more than before. Does that make sense?
Yeah.
That's the meaning of shifting to the right. Let's take another example. What will happen if hydrogen is removed from this reaction? A, B, C, or D?
A.
A is correct, yes. Shift to the left. It means the quantity of ammonia, will it go up or down at equilibrium now, new equilibrium?
It will go to the left.
It will there will be less ammonia now, right? Because shifting to this side. So there will be more nitrogen and hydrogen, less ammonia. Okay, so that's all about chapter 6. Thank you.
Does that same concept apply to when it's endothermic and exothermic?
Not exactly, but what do you have in your mind?
Oh, just like if there's heat added to a reaction, is it the same?
Heat, that's a different concept, because in those reactions, those are not reversible reactions.
Okay.
Okay, so heat.
So for those, like I should remember it?
Yes.
Okay.
Okay, so we will stop here. And if you have any question, please let me know. I will post this video also on Canvas, and you can go over it.
Okay, thank you.
Any other question?
So I want to know do we have access to your kind of slide, or it looks a bit different? I know it's from the text, but
when I post the video, so the slides are there.
Oh.
Okay, so you can rewatch it. All the videos with all the these chapter discussion videos are present in Canvas modules. You can go back and watch all previous videos also. This will be available today.
Oh no, I'm talking about the slides that you use. I know it's from the textbook.
Yeah, so some of them are textbook and some of them I, create. These are created by myself. So
Oh, okay. Okay.
if you need, I can provide these.
Yes, I think I would.
Sure. Yeah, I'll upload the slides too.
Thank you very much.
Okay. Okay. Thank you for staying, and I really appreciate your presence here. And hopefully you'll keep coming. Please let me know if there's any other question. Otherwise, we'll finish this meeting, and I'll see you guys next time.
Okay, thank you. Bye.
Bye bye.